Hello students, good time to all. I am Chandan Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss third law of thermodynamics and its consequences to unattainability of absolute zero, which is known as the NERNST'S heat theorem. Let's begin. We know that the change in entropy mathematically, that is ds is equal to dq by t. dq is the small amount of heat supplied to the system, t is the absolute temperature of that of system. So what happened? According to sign conventions of thermodynamics, means heat gained by the system is taken as positive and heat lost by the system is taken as negative. Hence, when heat is added to a system, means its entropy increases. Since entropy, here is the change in entropy, that is the change in heat. So when heat is added to the system, that indicates the entropy will be increases, and heat is taken out of the system, then the entropy decreases. If heat added, if here what we find from that of a expression, if heat added, then entropy increases, and if heat taken out, then entropy decreases. From this mathematical equation, we get that thing. When heat is added, then entropy will be increased. When heat taken out, then entropy will be decreased. Again, another mathematical form, according to the definition of entropy, we get S is equal to K times log W base E, where S is the entropy, K is the Boltzmann constant, and W is the thermodynamic probability. Here from that of equation, you see S decreases, then W decreases, means the thermodynamic probability decreases, means entropy decreases, and vice versa. Since entropy increases, accordingly the thermodynamic probability W increases. Now if S decreases, then W decreases. What happened here? If we go on cooling the system, if we cool that system, then its entropy will go decreasing. If we cool the system, that entropy will go on decreasing, and hence the thermodynamic probability W also decreases. Here you say S decreases, means the thermodynamic probability W decreases. How it decreases? Means we cool the system, we cooling the system, we achieve the decrease in entropy, and when cool it, accordingly when you cool the system, S decreases and W means thermodynamic probability also decreases. Thermodynamic probability W decreases. When we cool the system, S decreases, then thermodynamic probability also decreases, and the lowest value of thermodynamic probability W can be equal to 1. So the lowest value should be 1. for what? For W. The lowest value should 1 for W. That means W is equal to 1 with the lowest value. In case of Bose-Einstein statistics, in case of Bose-Einstein statistics, the minimum value of W, minimum value of W is equal to 1 is possible only when it means all the particles of the system must exist in the same energy. That is one possible when all the particles of the system must exist in same energy state, same energy state at that time the Bose-Einstein statistics should valid as thermodynamic probability will be 1. Again, in case of FD statistics, FD in the sense that is Fermi-Dirac statistics. Fermi-Dirac statistics, what we achieve, the thermodynamic probability will be the pi, that is the product symbol from I from 1 to k gi factorial divided by gi minus ni factorial into ni factorial. This is the definition of thermodynamic probability in case of Fermi-Dirac statistics. But when gi is equal to ni, when gi is equal to ni, that means that thermodynamic probability will be 1, W will be 1. Here the value of W will be 1 when all the particles of the system exist in the same energy. Here W will be 1 when gi is same as ni. Gi, ni, gi, that is the phase space or the number of cells. We can study the concept of Bose-Einstein statistics and Fermi-Dirac statistics in elaborately in case of statistical mechanics, but here just a concept to understand the thal of thermodynamics. Here W should be 1 when gi is equal to ni, which is minimum value of W, and hence we cannot cool the system further. That is the required expression or minimum value for cooling. Further cooling is not possible. Okay. In this case, particles indistinguishable. So in Bose-Einstein statistics, W is equal to 1 for that condition. Here W is equal to 1 for that condition, and we can further cool the particular system. So what we get from these different types of expression of entropy. So in that of overall scenario, we take the points. We write it. Thus, minimum possible temperature of system is 0 degree absolute, that is T is equal to 0 Kelvin. What happened at that case? Therefore, S, expression of S, that is K times, that is 0 degree Kelvin, here K log W base E. At that case, W will be minimum, means 1, the lowest value of W. So that is K log 1 base E. The value of log 1 is 0. That's why K into 0 is equal to 0. For what? For the entropy S. From this, we write, hence at S is equal to 0, at T is equal to 0, which is known as, this is known as third law of thermodynamics. Third law of thermodynamics. This is the third law of thermodynamics. At 0 Kelvin, we get the entropy will be 0, which is the third law of thermodynamics. To explain that, we follow that mathematical expression of entropies, and just a view how the thermodynamic probability useful to define the third law of thermodynamics. Now, the consequences to the third law of thermodynamics, which is known as the unattainability of absolute zero. Basically, that is the NERNST'S heat theorem. According to that theorem, absolute zero of temperature can never be reached by any physically realizable process. If we take various physical realized process, but we can't take the absolute zero that can be proposed by scientist NERNST'S. According to NERNST'S theorem, absolute zero of temperature can never be reached by physically realizable process. So how is it possible? Let we conclude. In thermodynamic processes, let we take two processes, like one is reversible process and another one is irreversible process, and we take into considerations of entropy and the change in entropy in these two processes, and we consequent that particular entropies towards the third law of thermodynamics, how we can't attain the absolute zero temperature. So let we take the reversible process here. Let reversible process, what happened? Let two state, let a reversible processes by which two states, one is state 1, another one be the state 2, is to be used to achieve absolute zero. These two states are used to achieve absolute zero. They need to achieve absolute zero. Then the entropies of initial and final states are given by the entropies. Let the entropies of initial and final states, the change in entropy here in case of state 1, the change in entropy, that is S1 at temperature T1 minus S1 at temperature 0, that is integration from 0 to T1, that is heat will be, let C P1 by T dt. Here the Cp1, that is the specific heat at constant pressure of state 1. Here is the dq by T. So, in place of dq I substitute Cp dt. That is for state 1, the change in entropy. Then for state 2, it will be the change in entropy, that is S2 at temperature T2, S2 at temperature 0 is equal to integration from 0 to T2, that is Cp2 by T dt. Here is the change in entropy in case of state 1 and change in entropy in case of state 2. But according to NERNST'S theorem, according to NERNST'S theorem, according to NERNST'S theorem, S1 at absolute 0 is same S2 at absolute 0 temperature, means the entropies of two states are same at absolute 0 temperature. Also, only an adiabatic process is accepted because there is no heat reservoir at lower temperature to accept heat from that of system. Since we consider here the reversible process, that is why we take also only adiabatic process. Only an adiabatic process is accepted because there is no such heat reservoir, no heat reservoir at lower temperature to accept heat from the system. Now, in adiabatic process, what happened? The change in entropy will be 0. In adiabatic process, the change in entropy del S, that is state 2 minus state 1 at temperature T1 will be 0 here. Now, let we put these values. So, therefore, we can say, putting these values here, S1 at 0 is equal to S2 at 0. What happened? That is same as that one. The change in entropies in that of adiabatic process will be 0. That is why we take here that section as we put this to that here. So, integration from 0 to T1, that is integration from 0 to T1 Cp1 by T dt is equal to integration from 0 to T2 Cp2 by T dt. Here if S2 is equal to 0, the entropy of that of state 2 is 0, then what happened? That particular integral will be 0. So, that integration from 0 to T2 Cp2 by T dt will be 0. Now, that equation changes to Therefore, that equation means integration from 0 to T1 C P1 by T dt is equal to 0. From these two, what we conclude, which is not possible, that is 0, that is 0, that expression 0, that expression 0. Is it possible? Which is not possible, which is not possible, because if the process starts with real positive temperature, real positive temperature, then that equation, then that equation can satisfied as Cp1 is greater than 0 at all temperatures. That is why, thus according to NERNST'S postulates, no simple adiabatic processes can lead from a non-zero to a 0 temperature, can lead from a non-zero to 0 temperature. We can't achieve that physical form in case of that adiabatic process. This is for what? This is for in reversible process. Here is we consider the two states of that of reversible process and take the entropy change and put it in case of NERNST'S theorem by taking the adiabatic process. Now, we take in an irreversible process, can we achieve the absolute 0 temperature or not? In irreversible process, let us take irreversible process. We may think that absolute 0 can be achieved by an irreversible process. So, what we get, since the entropy increases in an irreversible process, since the entropy increases in an irreversible process, therefore, the change in entropy, that is S2 at temperature T2 minus S1 at temperature T1 is always greater than 0, or that integral from 0 to T2 C P2 T dt is always greater than that integration 0 to T1 C P1 T dt, which cannot be satisfied at all if T2 is equal to 0, that is not achieved, which cannot be satisfied at all if T2 is equal to 0. When T2 is equal to 0, then it cannot be satisfied. So, look at this 2 one is reversible process and another one is irreversible process. From these two thermodynamic processes, we conclude that we can't achieve that absolute 0 temperature. So, we conclude that finally a conclusion is drawn here, absolute 0, hence absolute 0 is unattainable. We can't attain by a process that is reversible or irreversible. Even if it is repeated again and again, even if it is repeated again and again, but till we can't achieve the absolute 0 temperature. Absolute 0 is unattainable by a process that is reversible or irreversible, even if it is repeated again and again. So, with the help of this video lecture, we understand the third law of thermodynamics. How we get the third law of thermodynamics? By taking two mathematical equations to analyze at absolute 0 temperature, the entropy will be 0. And the consequences to that of third law of thermodynamics, which is known as the unattainability of absolute 0, that is basically NERNST'S heat theorem. And we take one is reversible process and another one is irreversible process, but finally we conclude, final conclusion, we can't attain the absolute 0 temperature. So, with this useful and informative notes, let me wind up this session. Thank you.